Good morning, students. Welcome to Bindu Dhadwal chemistry lessons. Our topic for today is physical properties of carboxylic acids and acidic character of carboxylic acids. Physical state: the first three members of carboxylic acids are colorless liquids and have pungent smell. The next six members are liquids with faint, unpleasant odor. And carboxylic acids having more than 9 carbon atoms are colorless, waxy solids. Benzoic acids and its homologues are also colorless solids. Solubility of carboxylic acids. Among the aliphatic acids, the first 4 members are very soluble in water, and the solubility decreases gradually with the rise in molecular mass. However, all are soluble in alcohol or ether. Benzoic acid is sparingly soluble in cold water but is soluble in hot water, alcohol, ether, etc. The solubility of lower members is due to the hydrogen bonding in which the carboxylic oxygen forms hydrogen bond with the hydrogen atom of the water molecule, and the carboxylic hydrogen atom also forms hydrogen bond with the oxygen atom of the water molecule. The solubility of aliphatic carboxylic acids decreases with the increase in molecular mass because of reduced polarity and hindrance provided by large bulky groups to the carboxylic group for taking part in the hydrogen bonding. Aromatic acids are almost insoluble in water but soluble in less polar organic solvents such as benzene, ether, and alcohol. Boiling points of carboxylic acids. The carboxylic acids have higher boiling point due to the presence of bonds, intermolecular hydrogen bonds. The oxygen of the carbonyl bond as well as the hydrogen of the hydroxyl bond of the carboxylic acid is going to form hydrogen bonds. As a result, the carboxylic acids exist as dimers. In fact, they exist as dimers even in the vapor phase and in the aprotic solvents. Carboxylic acids have higher boiling point than the corresponding aldehydes and ketones and even alcohols of comparable molecular masses. This is because as compared to alcohols, the OH bond in carboxylic acid is more polar, is strongly polarized due to presence of adjacent electron withdrawing carbonyl group. If this group is electron withdrawing, so electrons are pulled, oxygen feels shortage of electrons. As a result, this bond is more polarized and so hydrogen bonds are stronger bonds. Then the carboxylic acids form 2 hydrogen bonds, whereas alcohols are forming only 1 hydrogen bond. Carboxylic acids form dimers because of 2 hydrogen bonds. Among the monocarboxylic acids, the boiling point increases with the increase in molecular mass. Formic acid has lesser boiling point than acetic acid because with the increase in molecular mass, the van der Waals forces of attraction increase and therefore the boiling point increases. So, formic acid will have least boiling point, acetic acid will have more boiling point than formic acid, then propanoic acid will have still more boiling point, and butanoic acid will have greater boiling point. Melting points. The melting points of carboxylic acids increase irregularly with the increase in molar mass. For the first 10 members of carboxylic acid containing even number of carbon atoms is higher than the next lower and higher member containing odd number of carbon atoms. Butanoic acid will be having higher melting point than propanoic acid or pentanoic acid. X-ray diffraction studies show that acids with even number of carbon atoms have carboxylic group and terminal methyl group on opposite sides of the zigzag carbon chain. So they closely fit into one another, whereas the carboxylic acid containing odd number of carbon atoms, the carboxylic group and the methyl group are present on the same side, so they are not closely fitted, and so the melting point is less. In higher members, the melting point will increase with the increase in size of the molecule. The melting and boiling points of aromatic acids are higher than those of aliphatic acids of comparable molecular masses. This is probably because benzene ring of aromatic acid is planar and flat and fits more closely than zigzag chains of aliphatic acids. Chemical properties of carboxylic acids. So carboxylic acids, the chemical properties of carboxylic acids can be divided into 4 categories. A. Reactions due to hydrogen atom of carboxylic group. B. Reactions due to OH. One is reaction due to hydrogen of carboxylic group. Then second is due to OH of carboxylic group. Then third is due to the COH group as a whole. And fourth is reactions due to the alkyl group of carboxylic acids or the aromatic, the phenyl group of the aromatic acids. Reactions due to hydrogen atoms of the carboxylic group involving cleavage of OH bond breaks from here. So the first property is acidic character of carboxylic acids. This we are going to do in detail in this video. So carboxylic acids are distinctly acidic and ionize in water, forming hydronium ion and carboxylate ion. The strength of the acid will depend upon the extent of ionization, and it in turn depends upon the stability of the carboxylate anion formed. Both carboxylic acid and carboxylate ion are resonance stabilized. So this is the structure of carboxylic acid. Oxygen being electronegative in nature, the electrons move to the electronegative oxygen atom, and electrons of the second oxygen of the hydroxyl group will come to form a double bond to result in the second contributing structure, where oxygen acquires a negative charge and oxygen a positive charge with double bond. So if we see that in the structure 2, the oxygen atom of the hydroxyl group carries a positive charge. So the positive charge results in the attraction of these oxygen-hydrogen bonds towards the positively charged oxygen atoms, and the release of hydrogen ion becomes easier, and as a result carboxylic acid will give carboxylate ions and hydrogen ion. The carboxylate ion formed is also resonance hybrid of structures 3 and 4. This is when the oxygen atom is having negative charge, and its resonating structure is when the electrons move to here and these electrons move to this atom to form a negative charge on this oxygen atom and a double bond here. So the actual structure is in between the two structures, where the negative charge keeps on migrating between the two electronegative oxygen atoms. So both carboxylic acids and carboxylate ions are resonance stabilized, but if we compare these structures, it is obvious that resonance is less important in carboxylic acids than in carboxylate ions due to the following reasons. Number 1, the contributing structures of carboxylic acids are not equivalent, and in one of the structures there is charge separation. So these non-equivalent structures are of different stability. On the other hand, the contributing structures of carboxylate ions are equivalent, and therefore they must be of equal stability. So equivalent structures of carboxylate are greater stability as compared to that of carboxylic acid molecules, and the contributing structures of carboxylate ion have only negative charge, whereas that of carboxylic acids have positive as well as negative charge. Since energy is to be supplied to this molecule to separate the opposite charges, therefore this structure 2 is less stable than structure 1, and so we comparing all these factors, we can say that the carboxylate ion is more resonance stabilized than the carboxylic acid. So in this reversible reaction, as the product, the carboxylate ion is more resonance stabilized, the tendency of carboxylic acid molecule will be to move towards the more stable carboxylate ion product and give a proton as a result. So carboxylic acid is acidic in nature. The resonance in carboxylate ion is also supported by the bond length values. In case of carboxylic acids, we see that the bond lengths are unequal, whereas carboxylate ions, both the carbon-oxygen bond lengths are equal, 127 picometer. So the bond lengths, as studied from X-ray and diffraction studies, also support the equivalent structure theory of carboxylate ions, and therefore resulting in greater stability. The stability of carboxylate ion can also be understood in terms of delocalization of the pi electron density. The carbonyl carbon is sp2 hybridized and one orbital is unhybridized. This unhybridized orbital of carbon, the unhybridized p orbital of carbon can overlap with the p orbital of the oxygen atom, thereby forming a pi bond, and simultaneously this p orbital can also form a pi bond with the other p orbital of the oxygen atom. So the equivalent structure shows that the pi electrons are spread over both the oxygen atoms, and as a result the negative charge is delocalized. This delocalization gives stability to the carboxylate ion. Expressing strength of the carboxylic acids. The carboxylic acids are acidic, but they are weaker acids than mineral acids. The strength can be expressed in terms of their dissociation constant Ka, as carboxylic acid will dissolve in water to form carboxylate ion and hydronium ions. So the equilibrium constant Keq will be equal to concentration of products over concentration of reactants, that is concentration of carboxylate ions into concentration of hydronium ions upon concentration of dissociated carboxylic acid and water. Now, because water is in larger amount, its concentration is more or less constant. So this constant concentration can be taken to the left hand side and we get a new term, a constant equilibrium into a constant concentration is another constant which is called dissociation constant. So Ka will be equal to Keq into concentration of water equal to concentration of carboxylate ion into concentration of hydronium ions upon carboxylic acids. So this Ka value is generally called acidity constant because it can measure the relative strength of the acid, and the stronger the acid, the larger will be its Ka value. The dissociation constant can also be expressed in terms of their pKa values, where pKa is negative log of Ka. So the smaller the pKa value, the stronger will be the acid. Larger pKa value means weaker acid. In general, strong acids have pKa value less than 1, pKa value between 1 to 5. The acid will be moderately strong. If pKa value is between 5 and 15, it's a weak acid, and pKa value greater than 15 are extremely weak acids. Effect of substituents on the acidic strength of acids. The substituents have a marked effect on the acidic strength of carboxylic acids. The nature of substituent affects the stability of the conjugate base carboxylate ion and hence affect the acidity of the carboxylic acid. For example, electron withdrawing group will increase the stability of carboxylate ion by delocalizing the negative charge and hence increase the acidity of the carboxylic acid. Electron withdrawing group, for example chlorine, will pull the electrons towards itself. As a result, the oxygen feels deficient in electrons, and these bonds get attracted towards oxygen, thereby making the release of hydrogen ion easy. So a electron withdrawing group will increase the acidity of the carboxylic acid. Conversely, an electron donating group will intensify the negative charge on the oxygen atom and make the anion unstable. And electron releasing group will make the release of hydrogen ion difficult because oxygen gets electrons from this end, so will not take electrons from this end. So electron donating groups decrease the acidity of carboxylic acids. The release of proton from acetic acid will be difficult as compared to formic acid. In formic acid, there is no electron releasing group, so proton is released easily. But in acetic acid, this methyl group is electron releasing in nature. It intensifies the negative charge on the electron, on the electronegative oxygen atom. It will not take electrons from this bond, or the release of proton will become difficult, so acidity will be decreased. So in general, the electron releasing effect or plus I effect of alkyl group increases in the order. The bulkier the alkyl group, the more will be electron releasing effect. So methyl is less than, ethyl is less than, isopropyl is less than tertiary butyl. So acetic acid will be stronger acid than propionic acid, because propionic acid will have more electron releasing effect, which will be still stronger than isobutyric acid, and so on. So as we move towards bulkier alkyl groups, the acidic strength will decrease. On the other hand, electron withdrawing group or electron attracting groups do the opposite. Chlorine is an electron attracting group. It will show minus I inductive effect and withdraw the electrons from the carbon to which it is attached, and this effect is transmitted throughout the chain. As a result, the electrons are withdrawn more strongly towards the oxygen of the OH group, and the release of proton is made easier. Consequently, the acidic strength will increase. So chloroacetic acid will be stronger acid than acetic acid. Furthermore, because of electron withdrawing tendency of chloride ion, the carboxylate anion will be stabilized because the negative charge is dispersed towards the electron withdrawing chloride group. Then the effect of number of halogen atoms, more the number of electron withdrawing halogen atoms, more will be the acidic nature of the carboxylic acid. So monochloroacetic acid will be less acidic than dichloroacetic acid, will be less acidic than trichloroacetic acid. The nature of halogen atom also affects the acidic nature of carboxylic acid. The greater the electron withdrawing tendency or influence of halogen, stronger will be the acid. So fluorine group is more electron withdrawing than chlorine, than bromine, than iodine. So fluoroacetic acid will be stronger acid than chloroacetic acid, which will be stronger than bromoacetic acid, which will be stronger than iodoacetic acid. Then position of halogen atom. As the distance between the electron withdrawing group and carboxylic acid group increases, the electron withdrawing influence decreases. So 2-chlorobutanoic acid, the chlorine is close to the carboxylic group, will be stronger acid than 3-chlorobutanoic acid, which will be stronger acid than 4-chlorobutanoic acid, which will be stronger than the butanoic acid. So acidic strength decreases as the distance increases. Effect of type of hybridization of carbon atom bonded to carboxylic acid group. So direct attachment of groups such as phenyl or vinyl to carboxylic acid increases the acidity of the corresponding carboxylic acid. This is contrary to the expected decrease because of electron donating resonance effect. We say that electron donating group should decrease the acidity, but it's actually this vinyl group is actually increasing the acidity. The acidity is because of the hybridization of the carbon atom attached to the COH group. This is sp2 hybridized, which will increase the polarity of this bond, thereby increasing its acidic character. So larger electronegativity of the sp2 carbon atom of vinyl and phenyl group directly attached to carboxylic acid group will increase the polarity of the bond and thereby increasing its acidity. In general, acidity increases as the electronegativity of carbon atom directly attached to the carboxylic group increases. So a triple bonded carbon is sp hybridized. It will be propiolic acid will be stronger acid than benzoic acid, which has sp2 carbon attached to COH group, will be more acidic than acrylic acid, again sp2 hybrid atom attached to carboxylic acid group, which will be more acidic than acetic acid, and sp3 hybridized carbon attached to COH group. Benzoic acid is a stronger acid than acrylic acid because the double bond of benzene ring is less electron donating. This is because if it donates electron, the aromaticity of the ring is in danger. So in order to preserve the ring structure, it will not donate electrons, and so thereby it will be a stronger acid. Similarly, benzoic acid is more acidic than acetic acid because in benzoic acid, carboxylic acid is attached to sp2 carbon atom, whereas in acetic acid it's attached to sp3 hybridized carbon of methyl group. However, formic acid does not contain any alkyl group, so formic acid is stronger acid than benzoic acid, which is stronger acid than acetic acid. However, when a phenyl group is attached to a carboxylic group through one or more saturated carbon atom, then the phenyl group has a weak electron withdrawing inductive effect. Therefore, phenyl acetic acid will be slightly stronger than acetic acid. Phenyl group showing its electron withdrawing influence. In nutshell, electron withdrawing group withdraws electrons, disperses the negative charge on the carboxylate ion, stabilizes the carboxylate ion, and increases its acidity. Electron donating group intensifies the charge on the oxygen atom, decreases the stability, decreases the acidity of the carboxylic ion. The effect of acidity of following groups in increasing order of acidic strength is: phenyl is less effective, then iodo, then bromo, Cl, then fluorine, then cyano, then nitro, and then trifluoromethyl. Effect of substituents on the acidic strength of benzoic acid. So electron releasing groups like methyl, hydroxy, methoxy, and amino make benzoic acid weaker, while electron withdrawing groups like chloro, nitro make benzoic acid stronger acid. So amongst para substituted benzoic acids, para-nitrobenzoic acid is most acidic, than chloro. These are electron withdrawing group. Then benzoic acid. Then electron releasing groups decrease the acidity. So para-toluic acid will be more acidic than para-methoxy benzoic acid than para-hydroxy benzoic acid. And the substituent effect on acidic character of para-substituted benzoic acid: if the substituent is Y, then when Y is OH, the pKa value is 4.58. With methoxy, the pKa value is 4.48. With methyl on the para position, the pKa value is 4.38. With amino, it's 4.85, and benzoic acid is 4.20. Similarly, electron withdrawing group like chloro, the pKa value is 4, bromo 3.96, CHO 3.75, cyano 3.55, nitro 3.44. As we know, the smaller the pKa value, the more stronger the acid is. We will do more about this in our next video. If you like the video, please do share and subscribe. Thank you and have a nice day.